2021 program. We are very happy this evening to welcome a very distinguished speaker from the University of Antwerp, Professor Annemie Bogaerts. Annemie is a full professor at the University of Antwerp. She did her studies in the chemistry department at that university, then did a postdoctoral year in Florida, and since then she's been leading a very active group working in the area of plasma reactor design. She's the plasma catalysis with a special emphasis on CO2 conversion and plasma medicine applications. She's the author of over 350 peer-reviewed publications, including 11 invited reviews, as well as a number of invited book chapters, and has given large numbers of lectures invited at international conferences and obtained many prestigious awards in a large number of countries. For those of you who would like to follow up a little bit after the lecture, I might suggest that you take a look at an article which she wrote together with some colleagues in Chemical Reviews in 2015 on plasma catalysis, synergistic effects at the nanoscale. And she recently, in the Journal of Physics, Applied Physics, was the lead author of the 2020 Plasma Catalysis Roadmap. She is therefore eminently qualified to talk to us this evening on the subject of plasma-based carbon dioxide conversion. Annemie, it's a great pleasure. Can I ask those of you who are following the lecture just to make sure that your camera is not switched on so we don't end up watching some of you having your dinner. Annemie, the floor is yours. Thank you.
Okay. Thank you very much for the kind introduction. So, and I hope you can all see my slides. I think so. Can somebody just confirm that you see my slides?
Yes.
Okay, thank you. So first of all, I would like to thank the organizers for inviting me to give this talk here. Although it's online, so it's not as nice as when you see the audience, but I'll do my best. So the title of my talk is Plasma-based CO2 conversion, and the subtitle is The Hot Topic of Cold Plasma, because indeed, yeah, it's really a hot topic to study plasma-based CO2 conversion. So we all know there is the problem of global warming and our dependence on fossil fuels and the rising energy demands. And a solution for this is renewable energy, but this also comes at a cost, which means depending on whether there is a lot of sun and wind, there will be peak powers. So that's also, in fact, still a problem. Now, we think we have found a solution by converting the greenhouse gases, like CO2 and methane, into new fuels by using renewable energy. And then we call these solar fuels. And it's even better if we can use plasma for this. So that is the concept of our research, and more in general, plasma for electrification of chemical conversions. So the conversion of difficult or of inert molecules like CO2, nitrogen, and methane. That is more the general subject, in fact. But there is more research needed to understand the mechanisms, and we try to obtain this by computer modeling and experiments in our group. Now, before I go a bit further, I first want to explain you what is plasma, and then I'm talking about non-thermal plasma, and it's called a partially ionized gas, and it's also often called the fourth state of matter. So we all know there is solid, so there are three states of matter, being solid, liquid, and gas. So, and you go from solid to liquid to gas by heating the matter. But if you further bring in energy, either by heating or by bringing in electrical energy, you can end up with a plasma. So a plasma is an ionized gas consisting of neutral molecules, but also electrons and positive and negative ions. And the interesting thing of plasma for CO2 conversion is that the energy mainly goes into the electrons because they are light and they gain most of the energy from the electric field. And these energetic electrons will then dissociate inert molecules like CO2, nitrogen, and methane. So that allows thermodynamically unfavorable reactions to take place, which otherwise would require a lot of temperature and typically also high pressures. So there is no heating of the gas needed. We just, by using electricity, we heat up the electrons and they do the rest of the job. Now, there exists plasma in very different types. So this is the temperature of the plasma. This is the number density of the charged particles. And you can see here, we see here magnetic fusion reactors, the solar core, we see lightning, but the plasma types that we are studying are in this range here. So they're slightly above room temperature, and so like neon signs. Actually, you can divide plasma in two large groups. One kind are the natural plasmas, and in fact, plasma might not be so common here on Earth, but more than 99% of the visible universe is in plasma state. So we have the sun, we also have aurora borealis, for instance, we have the interstellar media, and we also have lightning a bit closer home. But plasma can also be created on Earth, and then we can still distinguish two large groups. The first group are the fusion plasmas, which operate at very high temperatures, so millions of Kelvin. They are very large. As you can see here, you see a man here. This is JET, Joint European Torus. And actually what they try is to build kind of suns on Earth. So try to mimic the conditions of the sun in order to create fusion as a future energy supply. And then there are also plasmas which are at much lower temperature. I write here room temperature, but this can also be up to 1,000 or a few thousand Kelvin. And this is called gas discharges. And that is what I will be talking on today. So a gas discharge in its simplest form is created by applying a potential difference between two electrodes. And the potential difference can be up to like 10 kilovolts, and it can be created in all kinds of gases and with pressures ranging from 1 Pascal to atmospheric pressure and even a bit higher. So you see here the two parallel plates, and this is the plasma created in between. And as I said before, important is that the gas typically remains near room temperature, and energetic electrons are created because they are heated by the electric fields that is created by this potential difference. Now there exist many different configurations. For instance, here we see plasma between two parallel plates. This can be just DC, AC, RF, or pulsed. This is an inductively coupled plasma that is also actually used a lot in analytical chemistry. Sometimes the plasma can be uniform, like you see here, but sometimes it occurs in filaments. This is a plasma needle. It looks like a little pen with a flame, but this is not hot, and it's used for plasma medicine applications. And this shows a tubular reactor. I will just have a little movie here. So this is the tubular reactor, for instance, we have in our lab for CO2 conversion, and you saw some filaments here. So yeah, because it exists in many different configurations, it's also used for a lot of different applications. And before I zoom into the application of CO2 conversion, I just give a very brief overview of other applications. For instance, in material science, for coating deposition and for surface treatment. And I have here a little movie for the improving the wettability of PET foil. So what we see here is we see, yeah, this was an advertisement of Vito. So we see it is put, so you see the plate, and that means the plasma, which you can see here in the movie, is treating the PET foil, but only there where the letters of Vito are present. So only there the PET foil is exposed to the plasma. So you see here when it's dark, you see that the plasma has a nice glow. So when we see now, when we take off this sheet, and then when we put some water on that PET foil, you can see that there where the letters are Vito, you see them clearly appearing. So the drops spread out, and where there are no letters, they are just as drops. So this is to improve the wettability. So in order to, like plastic bags, they have some text on it. That is to improve the wettability for ink on them. Then also in micro and nanoelectronics, plasmas are used a lot for chip manufacturing. In fact, more than half of the processes of the steps in chip manufacturing are based on plasma. Here you see a picture of the clean room at IMEC, and the plasma is behind this wall. And yeah, the wafers with the chips are then inside this plasma. And of course, because plasma also emits light, it is also used a lot for lighting applications, for instance, the fluorescent lamps. So it's based on excitation of atoms or molecules, and when they fall back to lower levels, they emit light. Sometimes this is UV light, but this can be then converted into visible light. Also neon advertising, xenon lamps in cars, and also plasma TVs are also based on the same principle that the plasma is emitting light. And it's based on a lot of pixels, and each pixel is actually a small plasma. Then another emerging application of plasma is in plasma medicine, and we also do a lot of research on this. So it is used a lot for sterilization, for dermatology, for wound healing, for dentistry, and also for cancer treatment. So, and in our group, we do a lot of research on cancer treatment. So this means in vitro work, but also in vivo work. And then the other large application, emerging application, is for environmental applications, for instance, for air or water treatment, because reactive oxygen species in the plasma, which are created first by the electrons. Electrons, for instance, activate the oxygen molecules so that, and they give rise to dissociation. The reactive oxygen species can then destroy volatile organic compounds like toluene, benzene, xylene. So we have the VOC gas. It passes through the plasma, and then it is ideally converted into CO2 and water, which are then less harmful. So, and often this is combined with a catalyst, as you can see on this picture as well. And then we speak about plasma catalysis. And this is to make the process more selective so that you form CO2 and water, and also more energy efficient. And then the big application on which we are working in our group is for sustainable chemistry. Because we know CO2, but also nitrogen and methane are inert gases, and the classical conversion requires a high temperature and pressure. That's what I said. So that requires a high energy cost. But if we can use a plasma, and as I said, the electrons are at high energy, the gas can be at room temperature, and we can activate the gas molecules by collision with electrons. So that is what you see here. You see CO2 and methane entering the plasma. These molecules collide with electrons. That causes ionization, excitation, and dissociation of the molecules. And these formed ions or excited species or radicals are very reactive. They can easily react with each other and form new molecules like CO and hydrogen. So this is called syngas, and it's used a lot in industry. Or it can directly form oxygenates like methanol, formaldehyde, formic acid, and so on, or higher hydrocarbons with high value. And these are then used as fuels or chemical compounds. So this means we can convert CO2 at mild conditions, just at room temperature and atmospheric pressure, by applying electricity over a gas so that we create a plasma. Now, the advantages of plasma for sustainable chemistry, there are plenty of advantages. As I just explained, the efficient breaking of the molecules. So the electrons will activate the molecules. And then actually the most efficient process is by vibrational excitation. I will come back to that later. And then you have a kind of non-thermal equilibrium because the electrons have a much higher temperature than the gas itself. And that makes the process so efficient. And plasma thus opens alternative reaction pathways, so at lower temperature, so just at room temperature for reactions that usually require very high temperature and high costs. It can use a flexible feedstock because it breaks up the molecules to the elementary species. It can convert CO2. It has wide opportunities for waste streams, also with a lot of nitrogen present, for instance, and this can even be beneficial up to, we found, by modeling we found, and also experiments we found, this is beneficial even up to 50%. Also, CO2 can be combined with a hydrogen source like methane, and then we speak about dry reforming of methane, or hydrogen, or water. So if you have CO2 and water, it could be called artificial photosynthesis. But it can also be used for nitrogen fixations to ammonia. So it could be an alternative to the Haber-Bosch process for ammonia formation, or also to NOx, which is then very interesting for fertilizer applications at a much lower energy cost than the Haber-Bosch process, theoretically, because we are still working on that to improve it. And also for methane coupling, for instance, to ethylene, which is also a process in industry that requires a lot of energy and emits a lot of CO2. So we can do this by plasma using electricity, and in this way reduce the CO2 emissions. Or for methane conversion into hydrogen, so for hydrogen synthesis and carbon black as an extra value-added product. And also the products are very flexible. It can be syngas with various H2CO ratios, or higher C hydrocarbons, or oxygenates. Another advantage, as I already said in the beginning, plasma uses electricity, and it can use renewable electricity instead of thermal energy. And because it is a fast switch-on, switch-off process, it is very useful to be combined with fluctuating renewable electricity. So for production and grid flexibility, and for production on demand. And it is a continuous process, so that is also interesting, with residence times ranging from milliseconds to seconds. It's a very simple design, so it has a low capex and no rare materials are needed. And it can also be used for upscaling. And the upscaling is actually done by numbering up, just by putting a large number of reactors in parallel. And in principle, it's just a linear scaling then. Different to, for instance, the Haber-Bosch process, which is only efficient at a very high scale. So it means that plasma can be fit to purpose. It can be used for delocalized production, for instance, in combination with a few solar cells or windmills even. So it can have a flexible production and energy demands. And here is a picture of such a plasma reactor in parallel, where you can see a large number of reactors in parallel, and this is an application for ozone generation at 100 kilogram per hour. Now, different plasma types are used for CO2 conversion. The first one is a dielectric barrier discharge. I will come back to that later. So another one is a microwave plasma, which is based on inserting microwave energy. And then another big one, where we are also doing a lot of research for, is a gliding arc plasma. And you have a classical gliding arc shown here at the left, which is between two parallel electrodes. But that has a disadvantage that it can only treat a limited fraction of the gas. And therefore, we are doing a lot of research on three-dimensional gliding arc plasmatrons, and I'll also come back to that later. Here I also have a little movie. So here we see that we have CO2 and methane. We put them in our plasma reactor. So here they are in the plasma reactor. We then apply electricity, which creates a plasma. As you can see here, it looks like lightning. And this will break up the molecules. So you see here, CO2 is split in CO and oxygen. And also the little yellow ones are electrons. And then methanol is formed and can then be used for new fuels. Okay, so then, if I come to the state of the art of CO2 splitting, a few years ago, we published a comprehensive review paper in Chemical Society Reviews with the state of the art of all the different plasma types that are used for CO2 splitting. And this is summarized in this picture here. So this shows the obtained energy efficiency as a function of conversion. So all the different symbols are different results, different papers from literature. Now what we see is that microwave and also RF gave the best results, even up to 90% energy efficiency. But this was obtained at reduced pressure and supersonic flow conditions, so at very specific conditions. And in fact, this was obtained in the 1980s in the former Soviet Union and actually was not reproduced since then. So it's a bit questionable whether these results can be reproduced. Then the gliding arc plasmas, so GA, are also quite efficient, even above this efficiency target. And we defined this efficiency target of 60% based on plasma to be competitive with other emerging technologies for CO2 splitting, and to be competitive with water electrolysis, which is a bit considered as a benchmark for electrification. It also uses electricity to split up water. And then based on that, so if the data points are above that, it means plasma for CO2 conversion is already competitive at this stage with the competing technologies and with water electrolysis. And the advantage of gliding arc is that it operates at atmospheric pressure, which is better to be combined with industrial applications. And then we also see dielectric barrier discharge and other. Other is mainly corona discharge. So yes, we also have a corona plasma. So we see that the energy efficiency here is only up to 15%. That was the best achieved in literature. This was in 2017, but in fact, even now, this is the best obtained now. But we see that this energy efficiency is a factor of 4 too low compared to this efficiency target. Now here I have a similar figure, but now for dry reforming of methane. It looks much more complicated because many more different plasma types have been used for dry reforming of methane. And also I plot here the energy cost instead of the energy efficiency. The reason is that the energy efficiency can only be obtained, can only be calculated if the reaction is exactly known. Like in the case of CO2 conversion, the CO2 is converted into CO and oxygen, while in the case of dry reforming, mainly syngas is formed, so CO and hydrogen, but also methanol can be formed and other oxygenates. So we don't know all the products, and then it's not possible to define exactly the energy efficiency, but the energy cost can always be defined. So the lowest energy cost here corresponds to the best energy efficiency. And we defined here again this green dash dotted line, which was then based on the same efficiency target of 60% in the case of dry reforming of methane into syngas. I come back to that later. So what we see is that for DBD and corona, again, the energy cost is a factor 5 too high compared to this efficiency target. Very striking is that for a microwave plasma, there are almost no results in literature, which is very strange in view of the very good results obtained for CO2 conversion. And the few results that have been obtained actually were at very high energy costs. We also see that gliding arc plasmas are actually performing quite well. Many of these points are above the efficiency targets and also above what would be obtained in case of thermal equilibrium. And they can be obtained, as I said, at atmospheric pressure. And then the figure also contains some other data points for spark discharges, like here, for nanosecond pulse discharges, and for atmospheric pressure glow discharges, which seem very promising, especially these ones here, quite low energy cost at a high conversion, but more research is needed, in fact, to further improve and to validate these results from literature. And we are also working on that, for instance. Now, maybe one thing to mention is that DBD seems not very promising if you look at this, but this is actually based on the formation of syngas, CO hydrogen, which is, there is some noise in the background. Okay, it's over. So, if you use a catalyst, and a DBD is most suitable to be combined with catalysts, you can, for instance, selectively form methanol, and methanol has a higher value than syngas. So normally you would go from syngas to methanol or a Fischer-Tropsch synthesis to go to higher value chemicals. And that process would also require energy. So if methanol or other oxygenates or higher hydrocarbons can be formed directly in the plasma by finding a suitable catalyst, then the energy requirement can be is not so strict, because then even a higher energy cost would be competitive with other technologies, because the other technology would, for instance, in dry reforming would produce syngas, and you would need extra energy to produce methanol, for instance. So in this review paper, we also made a benchmark with other novel technologies. And so you see here just thermal catalysis, electrochemical, solar, thermochemical, photochemical, biochemical, and then here plasma chemical. And actually a big advantage of plasma is the process versatility. So it can use quite different reaction feeds. It can be used for CO2 splitting, for dry reforming, CO2 hydrogen. CO2 water is not so ideal for now because the water seems to quench the plasma, but if you combine it with suitable catalysts, it still has good potential. So that still needs to be demonstrated. While a lot of these other processes just operate either in CO2 or with CO2 water, but not with such a flexible feedstock. Now, if we then look at the advantages and disadvantages of different technologies, so we see here traditional catalysis, catalysis by microwave heating, electrochemical, solar, and so on. So we see that plasma has a lot of green boxes here, which means it has a lot of advantages. It does not use rare earth metals. It uses renewable energy in an indirect way because it uses electricity. Some use it directly, just use the solar energy. It's a turnkey process, so it can easily be switched on and off. It has a high conversion and yield. I just move to this one. It can produce oxygenate products. It has a low investment cost, low operating cost, and a high flexibility. So it has many advantages, but the main disadvantage is that a separation step is needed. The reason is plasma is very reactive, but it also means it forms a lot of different molecules and not in a very selective way. And that's why if we can combine it with a catalyst, we can steer it to specific products. So that's the advantage of plasma catalysis. And also I need to mention that the energy efficiency actually depends on the reactor type. As I showed on the previous slides, gliding arc and microwave plasmas are more efficient than DBD plasmas, for instance. Now, the research that we do at Plasmant for CO2 conversion, we do experiments to improve the performance and also modeling for a better understanding. So we study the plasma chemistry. That means for pure CO2, methane and nitrogen, where we focus, for instance, on the role of the vibrational levels, because that can give more efficient CO2 conversion. We also study a lot of different combinations, as you can see here. So not just only with CO2, but also, for instance, nitrogen, hydrogen for methanol, for ammonia formation, and nitrogen, oxygen for NOx formation. We also, of course, study plasma catalysis in a packed bed DBD, and we have studied whether plasma can be formed in catalyst pores. This is, of course, very important, because if the plasma can be formed in catalyst pores, a larger area of the catalyst is exposed to the plasma. And we also study the interaction of plasma species with the catalyst surface by DFT simulations and microkinetics models. And then we also put a lot of effort on improving plasma reactor designs for different types of plasma reactors, DBD and packed bed DBD, microwave plasma, gliding arc plasma, and these atmospheric pressure glow discharges that I mentioned. Now, the experiments here I show a dielectric barrier discharge. So the idea is an electric field is created by applying a potential difference between two electrodes, and in between the electrodes we put a dielectric. So the name dielectric barrier discharge. And in this case we also put a catalyst in between, so in the gap where the plasma is, so the gas is moving in here and is coming out here. So in this case the gas moves in here and is then moving through this plasma reactor. I showed this picture before where you saw the plasma, the glow of it. But also gliding arc in various designs, atmospheric pressure glow discharge, and microwave plasma. And these three typically have a much better energy efficiency, but they operate at higher temperatures, even up to 3000 Kelvin, which makes that they are not so suitable to be combined with catalysts, because a DBD operates at or slightly above room temperature. So here we see a picture of a gliding arc, but I will come back to that later. Now this shows some results that we obtained for dielectric barrier discharge. So we see here the CO2 conversion and the energy efficiency as a function of the specific energy input. So the specific energy input is defined by the power over the gas flow rate. And we see a trade-off, because if we go to higher specific energy inputs, we get a higher conversion, but typically a lower energy efficiency. So these were results for an empty reactor, which means without packing, without catalyst beads. And the best results we obtained, as you can see from this figure, were obtained as 35% conversion, but at a low energy efficiency, or the highest energy efficiency was 8%, but the conversion was then only a few percent. So this shows the equation that we use for the energy efficiency. So this is the reaction enthalpy times the conversion divided by the specific energy input, and then the molar volume. Now we also studied CO2 conversion in a DBD by modeling. And then we see that the most important reactions are initiated by electron impact. So we have CO2, which gives electron impact dissociation into CO and oxygen. Also electron impact ionization into CO2 plus ions, which can then recombine and form CO and oxygen. And we also have dissociative attachment forming negative ions. So the take-home message is here that it's mostly electron impact, dissociation, ionization, and dissociative attachment. And these processes typically require a lot of energy. And that explains why a DBD is not so efficient. Now, how can we improve the energy efficiency of a DBD? That is by inserting a packing. So here we see an empty DBD with low energy efficiency. If we put a packing in, we get a much higher energy efficiency. And the reason is because the electric field and the electron temperature are locally enhanced at the contact points between these beads because of polarization of the beads. And here you see a result of the energy efficiency versus conversion, and the open symbols were in the non-packed, in the open reactor, and the closed symbols were in the packed reactor. So you see we obtain both a higher conversion and a higher energy efficiency. This is here also shown in this figure. So we see here for zirconia beads, 5 different sizes, as you can see here. So this is as a function of the packing bead diameter, and 3 different flow rates given here. And the dashed lines are the results without packing. So they are used as a benchmark. And we see that for beads larger than 1.4 millimeter diameter, the packing can give a result that is a factor 2 better than the empty reactor. For instance, if you see here. So the best result could reach a conversion of 38% and an energy efficiency of 6.4%. And these were among the best results that are obtained in literature, in fact. Now, I also said that the DBD still has a limited energy efficiency, so it is still quite low. And the reason why a gliding arc and a microwave plasma have a much better energy efficiency is due to the vibrational kinetics. So because CO2 can be very efficiently excited to vibrational levels. So this is seen here. So this shows the energy diagram. And we see here vibrational levels of CO2. And in a gliding arc and microwave plasma, we have especially vibrational excitation. That is because the energy, the electron energy in these plasmas is a bit lower. So they especially give vibrational excitation, which requires less energy. And then we have vibrational population of the higher levels gradually. We call this ladder climbing up to the dissociation limit, which is the bond energy of 5.5 eV. So this is a very efficient dissociation pathway. While in a DBD plasma, we have mainly electron impact dissociation, which goes to an electronically excited level, and that requires much more energy, like 7 to 10 eV, which is much higher than the bond energy. And that means that this extra energy is actually just wasted. So the CO2 dissociation by excitation of the lower vibrational levels, which then populate a higher vibrational levels, which we call ladder climbing, as you can see here, is the most efficient process and is especially important in a gliding arc and a microwave plasma. So this shows a gliding arc plasma that we developed in our group. And I have here a little animation of it. So here we see a picture of it with a plasma. We see here that we have a cathode, which is the reactor body, and this is the anode, which is the outlet. And then here, this is just an artistic view of the plasma. And we have tangential inlets. These tangential inlets, so here we see the gas flow pattern. So the gas has an outer vortex to the outside and then an inner vortex to the outlet. And in the ideal case, the inner vortex passes through the plasma. So the plasma is actually confined by the glow in the center. That is what you almost see in the figure at the bottom right. It's still stabilizing. This takes about 1 millisecond. So now you see it is stabilized in the center, and the gas actually passes through the arc plasma, and this gives very efficient conversion. I have here another static picture because sometimes the animations don't work. But what we see here is, so we see the gas has an outer vortex going to the end of the reactor body, and then an inner vortex to the outlet. And in the ideal case, it passes through the plasma. So this shows here the calculated electron density, which is the position of the plasma arc in the center. Now, this shows some results that we obtained for CO2 splitting in this gliding arc plasmatron, so GAP. We obtained a CO2 conversion up to 9% and an energy efficiency between 10 and 45%. And this was more or less independent of the specific energy input, which is striking because I showed for the DBD that the conversion was rising, but the energy efficiency was decreasing. And the best results were obtained at the smallest anode diameter, so the 7 millimeter. And that is because, maybe I can show this again. I don't know whether I can show this again, whether the animation starts again. Yeah. So you see the gas goes to the tangential inlets, and it first flows to the end of the reactor body because the anode outlet has a smaller diameter. And that's why these results, which have the most pronounced reverse vortex flow effect, so at the lowest anode diameter, give the best results. This shows a result in the same GAP reactor for dry reforming of methane. We see that we obtain a CO2 conversion of up to 24%, a methane conversion up to 60%, and an overall conversion up to 30%. And the energy efficiency we obtained was almost 60%. As you can see here, with an energy cost down to 10 kilojoule per liter, and these are very promising results. So you see the 60% we defined as the efficiency targets. Now, in the meantime, we already can do better than this. Now, we also found that this gliding arc plasmatron also has some limitations, and that's why we designed an improved reactor called dual vortex plasmatron. So we designed it based on computer modeling, and then we built it in the lab. It's based on 2 symmetric outlet electrodes to create a dual vortex, reverse vortex development. So in both directions. So the gas comes in here and moves into this direction and that direction. And the discharge is elongated in 2 directions, from here to there. So that means that we expect a longer resonance time and a higher conversion. And this result shows the obtained CO2 conversion and energy efficiency as a function of the specific energy input. We see again that the conversion rises and the specific energy input does not, and the energy efficiency does not drop. And we obtain an energy efficiency up to 40% and conversions up to 9.5%. We also had here an unstable region. This was due to limitations in the power supply. And we believe we can further improve. This is based on our model predictions. If we go to a higher power and flow rate, because then we can reach even higher conversion and we don't expect the energy efficiency to drop. But we have a problem with our power supply. It cannot reach higher powers. So this is a work in progress. And then the last example that I want to show for model-based plasma reactor design improvements is for an atmospheric pressure glow discharge. We first developed a basic design, and then we developed a design with gas inlets to create a vortex. That creates turbulence so that the gas passes a longer time through the plasma, has a longer resonance time, and also it gives a bit more cooling so that we can use a longer inter-electrode distance without melting, and we can use a higher power. And then we also built another design, which we call the Confined Design, where we have the plasma actually in a limited size. that was seen. For instance, you can see it here. So we put it confined so that now all the gas will pass through the plasma. And we expect a higher conversion, but we also have heat losses to the walls. And that is what you can see here. So we see the CO2 conversion and energy efficiency in these different reactors at 3 different currents. And we see here the basic design, which is the black bars here. They had a conversion of only 3 to 4%. Then if we tried with a vortex design, we reached up to 8% because we could use this larger interactile distance of 22 millimeter instead of 18 and use a higher power. As you can see here, this shows the power at the right-hand side. And that was the reason for the higher conversion. But then if we use this confined APGD, our reactor, actually the results confirmed what we could model, because we could obtain even a higher conversion up to 12%, which are very good values for a atmospheric pressure plasma. Because all the gas passes through the plasma, but the downside is that there are heat losses. So the energy efficiency, which typically is up to 30–35%, is a bit less for this confined design. So we are now looking for further improvements by improved turbulence, confinement of the plasma, but at the same time reducing the heat losses. So that's also work in progress. And then I come to the conclusion of my presentation. So I hope that I showed you that plasma technology is very promising for CO2 conversion and more in general for electrification of chemical reactions. So I already explained all the advantages, which are again listed here. So the idea is we put CO2, but also methane, nitrogen in our plasma reactor. We can use renewable energy to power the plasma, and we form CO and hydrogen, which can then be converted in chemicals and fuels, or directly into methanol and then used for chemicals and fuels. So then I come to the end of my talk. I want to thank all the people in my lab. So it's the Plasma Lab for Applications in Sustainability and Medicine, Antwerp, abbreviated as Plasmant. And I would like to thank you for your attention. Thank you very much. So,
thank you, Annemie. So if you have question, please, can you raise your hand and then I will mention your name so you can ask your question. Yeah. So Mr. Geoffrey, please.
Hello, I do have a simple question. What's the difference between a clean flame and a plasma flame? What would be the difference if there is one, or is there no difference at all?
So some people claim that a flame is also a plasma, but in fact there are some conditions to have a plasma. So you need to have a minimum number of ionization degree. So a flame is of course also hot and there is excitation, but typically not enough ionization to really have a real plasma with sufficient ionization degree. And a plasma flame,
how do you know you have sufficient ionization?
Sorry?
How in that case do you know you have sufficient ionization?
So this can be detected. There are different methods to measure the electron density in the plasma by Langmuir probes, for instance, or by laser scattering and optical emission spectrometry. And you compare that with the gas number density, and that defines then the ionization degree. So that's by diagnostics of the plasma.
Thank you. Next question.
I think the person is still muted.
Yes.
Who is the next person?
Oh, okay, Bo,
Yes, Bo, you're the next person. Sorry, I was
Okay.
as well.
Okay. Yes, we talked yesterday about graphene, and Bob said that it's produced with plasma, and it seems to be a very interesting new material with very good strength properties and lightweight. So can you develop a little bit about that?
Yeah, so indeed, there have been some research to produce graphene by plasma as well. We have done some research on producing carbon nanotubes by plasma. So yeah, it was just based on atomic level simulations, so we did not do it in the lab. And the advantage is because you have the reactive species, the carbon atoms, for instance, and they will react with a growing surface, and this will happen in a very controlled way so that you can have a certain chirality. Like you can have the perfect graphene structure, or for carbon nanotubes, you can also have very high quality carbon nanotubes produced by plasma. That is right, yeah.
Thank you.
Thank you. Can I ask a question? You mentioned that the great advantage of using catalysts was that you could get more selectivity. You didn't really develop that very much. Could you perhaps expand a little bit on that?
Yeah. The problem I did not say a lot about that is because there is not a lot of results about that yet. So in all reviews, and so it is claimed that plasma catalysis is very promising, and that is true. But at the moment in plasma catalysis, mainly thermal catalysts are used, and they typically, they do not give much better results than without catalysts, because then, so they don't really help the plasma process, because plasma is very reactive, and it already produces the reactive species, and you don't need this catalyst, in fact. But if we can develop catalysts which are tailored to the plasma environment, for instance, we know plasma creates radicals, also vibrationally excited species. And if we can design catalysts which can selectively exploit these properties of the plasma, then we hope that we can form, for instance, methanol in a selective way. For instance, we did research on ammonia synthesis, which is done a lot by plasma catalysis, and also on methane conversion into higher hydrocarbons like ethylene. And then we see that typically, if you are familiar with a volcano plot, which says what is the optimal catalyst, if you plot it as a function of the catalyst material, typically there is a competing effect. You don't want to be the catalyst to be too strongly binding, but strongly binding enough. And so then there is this maximum, typically, this volcano plot at the maximum. But in plasma, when you have the reactive species, the catalyst can be less binding. So you can go to more, to catalysts that are more, I don't remember the word, that are, that are less binding, let's say, more inert catalysts, for instance, and that can still produce very good results because they would release the product in an easier way. So, but more research is needed for that. We do a lot of research on that, both by modeling and by experiments, for instance, catalyst screening and characterization of the catalyst. But the ideal catalysts that can selectively produce, for instance, methanol has not yet been found.
No, okay.
So there's more research to be done there.
Thank you. Do we have other questions? Looking around. I wondered if you could also, perhaps you mentioned, I noticed this in the title of the group, that you work on medical aspects of plasma. Could you just briefly mention, you mentioned it at the beginning, and particularly said you were interested in this in cancer therapy.
Yeah. So what actually happens is a plasma, due to the electrons, creates reactive species. That's what I explained.
Yeah.
And for plasma medicine, it's especially reactive oxygen and nitrogen species, which are very important because, for instance, the plasma is operating in air, nitrogen, oxygen, and you create reactive oxygen and nitrogen species like hydrogen peroxide, nitrite, nitrate, peroxynitrite, OH radicals. And these radicals can, for instance, for the application of plasma of cancer treatment, selectively kill cancer cells, because cancer cells have naturally they have a higher ROS content.
Yes.
And when you add extra reactive oxygen species from the plasma, the cancer cells cannot survive that, while normal cells have a lower ROS content, and then adding this extra ROS from the plasma would not kill them. So that's why we do a lot of research on plasma for cancer treatment. But also here, more research is needed before we can bring this into practice. There are some clinical studies already, and for wound treatment, more clinical applications exist already, and also for sterilization. And actually, we are now having a project for treating coronavirus also by plasma. So we were contacted by the head of the intensive care unit of the University Hospital in Antwerp, because they have major problems, of course, with the pandemic, and for sterilization and disinfecting the beds. And plasma could be a very promising way for this, but also this requires more research, so it will not be for this pandemic, maybe for the next one.
For the next one, yeah. Yes, let's hope so. We have a question from Jeffrey.
Hello, I have another thought. In the area of plasma applications in medicine, as a young researcher, what advice would you give for someone for when you have an idea? What funding body is there to apply? What kind of funding is there to apply?
Yeah, so for plasma medicine, at the moment, it's not so easy because it is really interdisciplinary. So it's in between chemistry, physics, engineering, and then medicine. So typically we apply for interdisciplinary research, and also classical chemotherapy treatments, for instance. Plasma is still needs to be developed further. So people are still a bit skeptic about it, but actually this is the same as what we had about 5 or 10 years ago when we applied for funding for plasma for CO2 conversion. People also did not yet believe so much in it, so it was also more difficult to find funding. While now, I have a big ERC project, a synergy grant, and it is a bit more easier because there is a big need. And with plasma medicine, also more and more people are getting convinced, also many medical doctors. We have collaborations with several medical doctors who are interested in trying to apply this in the clinic. And we are talking with them and trying to develop even a clinical device. And actually, besides direct plasma application, just by using a plasma jet that you, for instance, apply to a tissue, this can be useful, for instance, for melanoma treatment or for dermatology. But if you would have internal cancers, internal tumors, this is more difficult to do with a plasma. But we have also found that if you treat liquids by plasma, you can transfer the anti-cancer properties of the plasma inside the liquid. And then you can apply that plasma-treated liquid to patients, and then you can use it for other tumors inside the body. So that's also something of interest for clinical applications.
Thank you.
Have we any other questions? Looking around. Yes, Boo, once again.
Yes, will you replace distilleries by making plasma alcohol?
So yeah, then we should make ethanol then selectively and not methanol then.
Yeah.
Yeah, in principle, if we would find a suitable catalyst for that, we could try that. But I think we are more looking into applications of biofuels and so on.
Yeah. I can understand why.
Yeah.
Well, if we have no more questions, let me take this opportunity once again of thanking you, Annemie, for a very interesting lecture. I hope you all enjoyed it. Our next activity will be in April, 22nd of April, my memory serves me right, when Albert Dijkstra will be talking to us about essential oils. And we look forward to seeing you all then. We also will have a further lecture before the summer by Nick Lane from University College London, who will be speaking to us in the month of May, I think 27th of May. So have a good evening. Enjoy the rest of your time with us next time, I hope. And we look forward to seeing you then. And meantime, take care. Thank you.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Bye. Thank you.
Thank you. Bye-bye.
Bye-bye.